Calculus BC, this is a little bit different. Rather than have an official lesson on a note sheet, our video here is actually doing the first homework problem on More on Integrals Worksheet 2. However, this problem is very, very important. It's extremely important because when you look at g of x, I'm going to recopy g of x up here. G of x is an accumulation function. It's going to say integrate from 0 to x. Then we'll have f of t dt. And of course, the t here is what we're going to call a dummy variable. We honestly could have any variable that we'd like. We could have a w, a u, whatever letter you'd like. We don't want to have x, though, because that would then get confusing with what we have for the upper bound. You see this upper bound, this x right here, if we were going to say g of x, we'd say integrate from 0 to x. So if we wanted g of 1, we'd integrate from 0 to 1. But we're going to say find that net area from 0 to 1 of this function. Now the graph of f is depicted here. The graph of f, as we read at the bottom here, the graph of f is consisting of two line segments. So let's find g of negative 1, g prime of negative 1, and g double prime of negative 1. Well, we'll get to that. We'll certainly work through that in just a moment. But my goodness, as we continue to press on, let's just think about this. What would a derivative look like? Just even symbolically. G prime of x. Well, remember what we've been doing. We can say plug in that upper bound into your integrand. You get f of x. And then we'd multiply by the derivative of x, which is 1 minus, then we're going to plug in this lower bound, f of 0, times the derivative of 0, which is 0. That completely wipes out. In other words, this is the wonderful thing when we even saw it on a previous note sheet. If you just have 0 to x, you can just pretty much plug that x directly into the integrand, and you're good to go. So g prime of x is equal to f of x. Wow, that's important. What do you think g double prime of x would be? Well, g double prime of x then would have to be f prime of x. So, wow, as we look through this, we can begin now to answer part A, and part A has three distinct little portions to it. It says, first off, could we find g of negative 1? Well, g of negative 1, like I was saying before, whatever you have for x right in here, that's what your upper bound is going to be. So this is going to be the integral from 0 to negative 1 of f of t dt. And as we're looking at that, well, my goodness, I'm sure kids are bothered by these boundaries. You're probably looking at that saying, wow, that just doesn't look nice. It doesn't look right. We've got our smaller number down below. So here's a property that we could definitely take care of. We can pull out a negative. Say it's the negative of the integral from negative 1 to 0 of f of t dt. And this integral from negative 1 to 0, well, tell you what, we're going to find the net area from negative 1 to 0 right in there. So, wow, as we're looking at that problem, you can see this is a triangle. It's a triangle with a base of 1 and a height of, well, you can see it goes up to 3. And this area of a triangle is going to be, of course, 1/2 base times height. So that's going to be 3/2. But don't forget, you've got that negative out in front. So it's negative 3/2. That's what g of negative 1 really is equal to. Wow. Well, let's keep going. As we progress, we can say, what's g prime of negative 1? Well, g prime, look, real quickly, we could say g prime of x was equal to f of x. So if I'm going to be looking for g prime of negative 1, I'm really saying what's f of negative 1? And f of negative 1, it's simply the y value that we have on this curve f right here. You can see this is the point negative 1 comma 0. So g prime of negative 1 is just going to be a 0. So here's my first answer. Here's my second. And then we're going to say, well, what's g double prime? Well, that's right up in here. We could say, well, look, g double prime of x was f prime of x. Meaning if I found g double prime of negative 1, that's f prime of negative 1. And you can quickly see that f is not directly, f prime is not directly shown here, but what you're really saying is what would the tangent line slope be? If I were to draw in a tangent line right in here, well, it's going to be the same slope of this segment. You can see going from the x-axis at negative 1, 0, we're going to go up 3, we're going to go right 1. So this is going to be 3 over 1. So g double prime of negative 1 is equal to 3. This threefold question gets repeated quite often. It gets often a lot, actually. And we really have to be prepared for it. It's throwing together a first derivative, a second derivative, and the original function. So that right there is going to show up a lot on the actual AP exams. These accumulation problems can show up quite frequently. What we're going to be addressing next is for what values is G increasing. We'd also like to know when G is perhaps decreasing. We can answer that as well. I know they're not specifically asking for that. For that matter, we could try to find out when G has a maximum or a minimum. So let's think about this. If I were to say when is G increasing, well, you know what you're going to be doing, guys, is you're going to be looking at the first derivative. So I'm going to put part B up here just so that we can look at this. We're going to say G prime of x, which is equal to f of x. You know, when is G increasing? G is increasing when G prime of x is greater than 0. So I'm interested in finding out where f of x is greater than 0. Well, I hope as you're looking here, we can erase this a little bit. I hope you're looking at this and you're saying, well, wow, where could we be having our f values greater than 0? It's where your f curve is above the x-axis. So it's here. Remember, intervals of increase, we're always going to use closed brackets. So we'll say that's from negative 1 to 1. So G is increasing on this closed interval here. Now, by the way, I think it can be very, very helpful if we begin to read ahead. And by the way, we are going to have to first explain our reasoning, forgive me. G is increasing here because, why? G prime of x is greater than 0 here. That's our explanation, isn't it? But listen, as we're trying to expand a little bit here, a lot of times we look at our first derivative and ultimately what we're trying to do is find out if there's a relative max or a relative min. And I think that can be very, very, very helpful. In fact, I'm going to go off to the side just right over here and address that. We're interested in finding extrema for G. You can think, why are you even doing that? I'm reading ahead. If I'm going to have to graph, if I'm going to have to make a graph of a function, I'd like to know where my high and low points are. So I'm interested where g prime could be 0. I'm going to find where g prime of x, which by the way, that's really f of x, where that equals 0. And I hope you can see it's here at 1 and negative 1. So I have here's 1 and here's negative 1. And we already said that g prime was positive between negative 1 and positive 1. But I hope you can also see that if we extend out to 2 and negative 2 here, g prime was negative there. Why? Because that's where we're below, where f is going to be below the x-axis. So g prime, which is f, when that's below the axis, that means g is decreasing. But look at what is happening, guys. You can see that you'd have a local min and a local max. And you can even jot that down off to the side here. We'd expect to see a local min at x equals negative 1. We'd expect to see a local max. And again, this is for g of x. Right here, we'd have a local max at x equals positive 1. Wow. So that's all well and good. That's hopefully helping you out some. Let's real quickly see where we're going next. You're going to also, for part C, address when g is going to be concave down. For that matter, maybe we should find out where g is going to be concave up. I think we should do both, shouldn't we? I mean, if we're going to be graphing in a little bit, we might as well. So let's think about concavity. Let's think about points of inflection. And that's where we'd like to find out where g double prime of x equals 0 or undefined. And g double prime, guys, is really f prime. Remember, g double prime of x is equal to f prime. So looking at this picture where you have f, where would f prime, where would the tangent line slope be 0? You'd say, well, nowhere. You never flatten it out. But at x equals 0, that's where you're going to be undefined. F prime of 0 is a corner point. That's undefined. So you can see you've got positive tangent line slopes here. You've got negative tangent line slopes there. So I could real quickly write this out, and I could say, hey, I know that at 0, I've got a potential candidate for an inflection point. And I know if I were to go to the right of 0, I have a negative second derivative for g. That's where f prime right here is negative. From the right side, f prime, over here from x negative 2 to 0, f prime would be positive. I'd have positive tangent line slopes. So that's what g double prime is. G double prime is f prime. So g is concave up from negative 2 to 0, and it's concave down from 0 to 2. So it's at this point where we can more or less answer what's happening with part C. With part C, just trying to squeeze this in, when is your curve concave down? G is concave down on the open interval from 0 to 2. You'd say, well, why is that? That's because g double prime, which equals f prime, is negative on that interval. So, of course, we're also going to have a point of inflection for g at 0, at x equals 0, because concavity changes. We're going to stop here and see if we can pull all this information together and see if perhaps we can make a graph.